So, well, I'm professor at the University of Seville. I'm Luis Tavara, and this work was done in collaboration with some of our colleagues at the University of Seville. So our aim on this work was to present a new crack tip element, especially designed for working on mode-free, on cracks on mode-free. Our aim or the objective of these studies is in a broader connection, because we are interested in interface cracks, which may appear in different locations. Especially, we were working on composites for several years. So we have seen these interface cracks, for example, at micromechanical level. At micromechanical level, at mesoscale, and also at macro scale. So the presence of interfaces are very interesting when we're working on composites. So from a numerical point of view, it's quite interesting also to understand how the cracks works when we are on this kind of interfaces. So there are several techniques, several models to try to understand how crack works on interfaces. One of them is the modeling of the interface with a spring distribution, which is usually called weak interface, sometimes also linear elastic interface, and many other names. But basically, there is a distribution of the springs. These springs can have different combination of behaviors, normal and tangential behavior, but it has a drawback. The main drawback of this model is that when we have stiff interfaces, the singularity that may appear on the crack tip lead us that we have also a singularity on the zone, the vicinity of this crack tip. From a numerical point of view, this means that we need much more refined meshes. And from a computational cost point of view, we have much more time. So the aim of the idea is to present a new element which avoids these problems. Going from the very basic of this spring interface model, we have this spring that may work also on normal and tangential behavior, so which is very well used. We have a lot of results that have solved this problem. But as I said before, the main drawback is when we have stiff interfaces. So what we are presenting now, we are focusing only on the antiplane shear condition, which is basically the joining of two solids between an interface, and we have a crack in the middle, and the boundary conditions are working as antiplane shear. The way we propose the new element is based on the analytical solution very recently proposed by Jimenez and Mantic in 2023. And the aim was to include these solutions within the finite element the new crack tip element. So the main ideas were, or the main contribution of this work is that we have these singularities associated to logarithmic and also some R, the radius directly associated to the solution. So this term should be included on the element in order to have an accurate result. So the way we proposed these singular shape functions was to include these behaviors associated to 1 R and R multiplied by logarithmic of R. And using these base functions, we proposed some new shape functions for the element. So we started with a 1D behavior, just only on 1D, and we propose these shape functions. The next step would be to go on and move this to 2D. And we started on a quadrilateral element, which was basically a 4-node element where we include a middle node in order to include the new shape functions. The next step was to collapse the element, the quadrilateral element, into a triangular one. Then node 1 and 4 collapsed into the same position. And at the end, the tip of the crack tip should be in position 1. So we will have the radial behavior associated to the crack. Based on the previous functions I showed you for the 1D, we propose these ones for the 2D. And basically, the ones that are associated to the behavior are associated of the displacement shape functions. The geometric shape functions remain the same as the linear element. And what we are presenting now is the results we obtained for this problem. We have two configurations. As we already have an analytical solution of this problem, we propose a first problem where we impose the solution, the analytical solution of a problem for all boundaries except for the robin part, for the spring part. And we chose 3 different type of meshes. As you see, all the elements that appear in the different configurations are classical linear elements, except by those that are shown red. Okay, those are the ones that have the new shape functions. And also, we increase the number of elements. We made an edge refinement in order to avoid any other effect. And we increase the number of elements that appears in this region. So the results we obtain, we can compare, as I said before, with analytical solution. As we can see here, the convergence of the solution is quite fast, especially for the singular elements. If we go closer to this song, we may see here that although here we can see that it seems that we are perfectly matching everything, if we go closer, we may see that the analytical solution is still not yet, we are not yet on the analytical solution, but we are quite closer, even with very small number of elements. Another interesting thing is that if we see these results, the continuous lines are the one obtained with a singular element we are proposing, and the one with the dotted line is the one with the standard elements. If we go further, and we also check the different 3 types of meshes we are studying, we can see in this plot the different errors we obtain with a different number of elements in this song. So as we see, we are in a logarithmic scale, so we are talking about order of magnitudes of differences on the results. And one of the very interesting things that we can see is that first, all the solutions obtained with standard elements that are with the ones that are empty in the middle are here in the upper part, which means that the error is higher. While the results obtained with the filled dots are on the dotted on the lower part, which means that the error is lower. Here we set up a parameter, what we call improvement parameter, which is basically the ratio between the error obtained with the standard elements obtained versus the ratio obtained with the singular elements we are proposing. And as we see here, the improvement is always higher than 1, which means that the results obtained with the singular elements are much better than the ones obtained with the standard elements. The other problem we try is the one usually associated with a tensile loading, but in mode 3. So we are having a load which is out of the plane, and we have a symmetry plane here, and also we have a crack. So basically, we have once again, the 3 different type of meshes we have here. We are once again increasing the number of elements in this robin edge. And we also define a dimensionless parameter, which we call delta, which is mainly associated with the stiffness of the interface. If delta is low, it means that the interface is very ductile, say. And if we, sorry, which will be the same. Okay, if it's higher, it's stiffer. And the higher delta it is, the stiffer is the interface. In fact, for an infinite value of delta, we may get to that perfect interface condition. So results obtained with a different type of meshes are very similar, but we are focusing first on this type of configuration, of this type 1 configuration. And here, as we don't have an analytical solution, what we are comparing is comparing with a very large number of elements. So we are thinking that if we have a very large number, we are approaching to the correct solution. So if we see the results here, once again, the results obtained with a very large number are the ones that we are getting as good results. And as the number of elements are increasing, the results are approaching to those results. If we go closer, and also if we increase the stiff of our interface, the results we obtain tends to go to the classical crack solution. In fact, if we remember the classical solution of a crack, this displacement solution is very classical in fracture mechanics. So we see, for example, that when this stiff, this delta parameter is higher, the stiff, also the displacement here on the spring interface is almost 0. So it means that we are almost close. And once again, the results tends to the solution of the very large number of elements. If you go the same study with a different configuration, a different mesh, we can see that the results are basically the same. We have a very similar solution. Once again, if we go once again with a very stiff interface, we can see that the solution also tends to the very large number of elements. If we go to the convergence study for different values of delta, it means we are having stiffer interfaces as we are going down. For example, for delta equal to 10, we have the green here line. With 1000, we are closer to the crack. And also we are presenting here the solution for the crack, the analytical solution. So as we see here, we are getting to the solution when the interface becomes very stiff. These results appears once the same from the different type of meshes we are presenting. The results are basically the same. We have different conclusions, but at the results are basically the same. So if we go once again with the error, now we don't have an analytical solution, but we can have a relative error associated with a finer mesh. So we define this relative error, which is basically the displacement at the crack tip minus the displacement at the crack tip, but using the maximum number of elements. And we have this relative error. So once again, which is interesting that when the delta value is small, we can see that the results are very similar for the standard and singular elements. Nevertheless, the singular elements are always better than the standard elements. But when we go for stiffer interfaces, we can see that the results start to get different, much more different. Moreover, if we go with this very stiff interface, we can see here, for example, that the standard elements got the solution, while with the new element, the new singular element, we have almost 1, 2, or 3 order of magnitudes of different errors. So we get to a convergence very much faster than using standard elements. If we go to the solution of the stresses at the crack tip, we can see once again very similar results. Stresses can be reached easily when the interface is not stiff. But once again, if the interface becomes stiffer, let's go directly to 1000. We can see, for example, that with singular elements, we reach to a convergence value much more faster than with standard elements. So finally, as conclusion, we have proposed now a new singular element that we have developed based on asymptotic solution proposed for this weak interface. This new element allows to model interface crack without the use of using excessively refined meshes at the crack tip. And as results have shown, this new element improves considerably the results with the standard elements. And just finally, I want to thank you the funding of these projects. Thank you very much.